Welcome to the next video. As we will be continuing the discussion of the DPM, that is discrete phase modeling, I really thought it is something important for us to discuss what is mentioned in ANSYS manual because they are the main creators of the software and we must definitely go through the data what they have provided, especially with respect to the introductions of different models in ANSYS Fluent. Now, before discussing about this thing, I really want to go back to our geometry what we have. And in order to understand the DPM functionality, I will be using the same model over here. In fact, the same simulation what we have performed in the previous video, or we have concluded in the previous video. Now, we can imagine a case over here. For example, this pipe is fitted in some petrochemical industry. Okay, just imagine in that way or petrochemical site, and the fluid inside this pipe is propane. Okay, that means the working fluid in flow simulation is the propane gas. And what we will be doing is we will be injecting a few amount of or certain amount of droplets of water in the propane gas. Okay, I mean, as the gas is moving from left to the right, we will be injecting certain amount of material. I mean, we will be injecting the water droplets into this gas, right? Now, according to me, I'm not really sure because I don't belong to the field of oil and gas, but according to my knowledge, I believe I've read that the injection of water droplets is happening. I mean, they perform this injection in the pipes to dissolve any salts in the gas stream. Okay, for that purpose, they inject the water droplets, right? But what we will be doing is we will be simulating and seeing how these water droplets are carried by the gas flow. Okay, when the water droplets are injected, how are they carried with the gas flow? And we will also analyze to what extent the water droplets may impact the pipe, right? So we will be understanding all these things with the help of discrete phase modeling or discrete phase simulation, you can say, right? And what are the different things that we will be learning within DPM? That is, we will be learning how to define the particles or the material of the particle. Then we will also see how we can inject the droplets at certain speed or certain velocities in certain directions from certain surfaces. And we may also include the turbulence effects. Okay, we can also add up the turbulence effects. And we can also as I've mentioned to you a while ago, that we can analyze the impact of water on the pipe wall. So we can just analyze the erosion or corrosion what is happening on the pipe with respect to the presence of water droplets. So all these things can be covered with the help of DPM. These are not the only applications of DPM, and there are wide applications of DPM which we can find. And now I'll just take you back to the browser, and we will see what is mentioned in the introduction of DPM. Now you can see that the advances in computational fluid mechanics have provided the basis for further insights into the dynamics of multi-phase flows. And currently there are two approaches for the numerical calculations of multi-phase flows. That is the Euler-Lagrange approach and the Euler-Euler approach, right? So we have these two approaches which are being followed or which are standard for calculating for performing the numerical calculations. Clear? So the DPM or the discrete phase model adapts the Euler-Lagrange approach. Okay, I'm not sure how do you pronounce this. Is it can be Lagrange or Lagrange? You can just check up that thing. And what is this particular EL approach? Let me just call it as EL. And in this approach, the discrete phase model in ANSYS Fluent follows the Euler-Lagrange approach. Okay, and the fluid phase is treated as continuum by solving the Navier-Stokes equations. Okay, so you can just imagine that we have just now solved the Navier-Stokes equations or the RANS equations by keeping the working fluid as propane gas. Okay, so that is what is considered as the first phase, that is the fluid phase. The next phase is the dispersed phase. So in this approach, the dispersed phase is solved by tracking a large number of particles, comma bubbles or droplets through the calculated flow field. So this is a combination of fluid phase plus dispersed phase. The fluid phase in our case will be the propane gas continuum model what we have completed so far, and the dispersed phase will be the water droplets injected into this continuum, uh, and uh, and understanding, I mean, after injecting we will be tracking the large number of particles of those water droplets into what, through the calculated flow field, right? So this is what is about the simple procedure. This is the simple explanation of this approach. And the dispersed phase can exchange momentum, mass and energy with the fluid phase. This can happen if there is an option to do that. Clear? And I really request you to try to understand the first para, because that is most important. Okay, this will basically make you understand what is happening in the DPM and what is the procedure in DPM. Okay, and there are two phases. The first one is the fluid phase, the second one is the dispersed phase. Fluid phase is solved at first. Okay, that is what we have done in our T pipe case. We have solved the propane gas movement. Okay, and now we will be performing this simulation for dispersed phase. And this simulation is basically nothing but the tracking of large number of particles or droplets or bubbles into the calculated flow field. So this is the calculated flow field what we have, and we will be just analyzing the particles. And let us just continue. The particle or droplet trajectories are computed individually at specified intervals during the fluid phase calculation. This makes the model appropriate for the modeling of spray dryers, coal and liquid fuel combustion, and some particle laden flows. So these are the different applications of DPM. And there are certain limitations. We can just go and see if you want over here. And limitations on particle volume fraction, limitation of modeling continuous suspension of particles, limitation on using the DPM with other ANSYS models, right? So obviously, I mean, in ANSYS Fluent, there are plenty of models which are present over here. You will be having the multi-phase models, okay? The energy, the viscous turbulence, the radiation, heat exchanger species, DPM, etc. So each of this model has their own benefits and their own limitations. So it is upon the user to consider those limitations or applications and perform their job. So that is what we are going to do at this stage. And at this moment, I think, I mean, this brief introduction is sufficient for us, and I will be attaching this link in the, what do you call, in the resources. You can just go through. So these are the equations for particle force balance. And if you are trying to present some report, you definitely have to add up the equations. If your case is involving a DPM study, then you have to add up these equations of forces as well, right? So ANSYS Fluent predicts the trajectory of discrete phase particle or the droplet by integrating the force balance on the particle. Clear? Which is written in the Lagrangian reference frame. This force balance equates the particle inertia with the forces acting on the particle, and can be written as follows. This is all technical thing which we are not diving into, because this will take a lot of time for us to understand. But I really recommend you to read up and catch up what are the terms. Okay, and that will be very helpful for you. So these are the different forces: Safman's force or Brownian force, and you'll be having one more over here, yeah, thermophoretic force. So if you want to include all these forces in your particle disperse phase calculation, then you just have to turn on over here with a simple tick, and these equations get activated in the background. Clear? And let us just pause this video, and now let us just move to the next video and perform the technical setup over here.